Hi, and welcome to the third tutorial video for this term. There are two problems for this week, but the first question has two parts. The first problem states, each of the two blocks has a mass m. The coefficient of kinetic friction at all surfaces of contact is mu. If a horizontal force P moves the bottom block, determine the acceleration of the bottom block in each case. This is a pretty basic dynamics problem. We just have to draw a few simple free body diagrams. Let's start with part A. I'll draw the free body diagram for block A on the left and block B on the right. For block A, we have the pulling force P, a force due to gravity, normal contact forces from both the floor and block B, and two friction forces at those points of contact. Remember that friction forces always oppose the direction of sliding, so in this case they both point right. Next, we will write two F equals ma equations. One will be for x and the other for y. I'll assume that x is positive rightwards and y is positive upwards. The sum of forces in x is equal to mass times acceleration in the x direction. In this case, the acceleration of the block is purely in the x direction, so I'll write a sub a instead of a sub x. The forces acting in this direction are the friction forces as well as the pulling force. Remember that rightwards is positive. We can do the same in the y direction, but the forces will sum to zero since there's no vertical acceleration. Then, we go through the same process for block B, which has a force of tension rightwards from the string. Block B doesn't move at all, so the forces will sum to zero in both directions. In the y direction for block B, we can simply see that N2 is equal to mg. We can ignore the x direction for block B, since it would only be useful to tell us about the tension value in the string. We don't care what the tension is, so we'll ignore this equation. Next, we can find N1 using the y-coordinate equation for block A, since we now know N2. It comes out to 2 mg. Substituting all of that into the x-coordinate equation for block A, we can rearrange, and find that the acceleration is 3 mu g minus p over m. Again, assuming that rightwards is positive. Moving on to part B, the problem now involves this pulley. When you deal with a pulley problem, you want to think about the lengths of each section of string. Here there are two lengths, and we can call them SA and SB. The two lengths describe the total string length, L total. My dynamics professor at Waterloo always called this the law of conservation of string, which is that the total length of string is always unchanged. If we take the second derivative, we end up with the following expression. The accelerations of the two blocks sum to zero. Let's keep that fact in our pocket and move on to the rest of the problem. The free body diagram for block A looks much the same as it did in part A, but with the addition of this new tension force from the string. As for block B, its free body diagram is exactly the same as it was in part A, but now it's allowed to accelerate, so we need to make sure we include the acceleration term. We find N2 just as before, and keep it up here with our other useful information. Same goes for N1. Now, remember the conservation of string result from before? We can use that to replace a sub b with negative a sub a, and then move the negative sign to the other side. Now these two equations left on the screen are both expressions for m times the acceleration of block A. If we equate them, we can solve for t. Plugging t back into either of the two equations gives us the acceleration of block A, as shown here. And that's the answer to this problem. Now for problem 2. It states, the particle has mass m and is confined to move along the smooth horizontal slot due to the rotation of the arm OA. Determine the force of the rod on the particle and the normal force of the slot on the particle when theta equals theta 1. The rod is rotating with angular velocity theta dot and angular acceleration theta double dot. Assume the particle contacts only one side of the slot at any instant. Here's a little diagram of the problem. We have r, which is the length to the particle, as well as theta, which is at 30 degrees. There's also h, which is this vertical distance here. The problem also gives us the angular speed and acceleration of the bar's rotation. This is a clue that we'll want to use cylindrical coordinates for this problem. The expressions for accelerations in cylindrical coordinates have the terms r dot and r double dot in them, so we'll want to figure out what those are. We can start by finding r using some basic trigonometry and find that it's 0.58 meters. Then, we can take the derivative of this expression for h, and isolate r dot in the result to find that r dot is 0.67 meters per second. Taking the derivative again, we can isolate for r double dot and find that it's 4.85 meters per second squared. Great, now we have values for r dot, and r double dot. Next, we can draw a free body diagram for the particle with the r and theta directions. There's a force due to gravity, a normal force from the rod, and a normal force from the slot. Let's write the sum of forces in the r direction and substitute in the expanded expression for radial acceleration. We can isolate for F sub n, which is the normal force from the slot, and find that it's 6.37 newtons. We can also sum up the forces in the theta direction and substitute in the expression for angular acceleration. Isolating for the normal force from the rod lets us find that the force is 2.93 newtons. This problem might have looked imposing at the start, but ultimately it wasn't too bad. The keys were to recognize that we could use cylindrical coordinates, and to figure out how to get expressions for r dot and r double dot. So that's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.